Okay, then last experiment, I will disconnect here everything once again. And as some last thing, we can, as said, measure this filter. So the probe to measure the input voltage needs to be connected. The source needs to be connected. And these are the probes for the output. So one at the upper potential and one at the lower potential or lower terminal. Not too solid, but okay. And let's hit go. And see what it does. And at least we start with some meaningful gain at around 0. And so this is the filter that we measured before. Unfortunately, there is no corner frequency or something like this given directly on the sticker. So we would need to check the data sheet of this to find out what this is. But okay, here is something more. It's a line filter, but also no more values. And I think there's the very same sticker here on the other side. Yeah, and of course the fluctuation of this curve is somehow noise. Okay, here also something interesting happens. There's some increase, so there's some kind of attenuation. No, there is some kind of gain. I think this is somehow looking meaningful. So the question is, where does this gain come from? No. So this filter in a certain frequency range even amplifies the signal, at least for this open circuit measurement case that we do right now. And then we get some attenuation and then it's going down. And the phase, as you can see, is starting with 0. The phase does not do too much, but then the phase is going to minus 180 degree. And here at this resonance, we have something like minus 90 degree. And yeah, so I think this is somehow meaningful. This does not look too bad. If we would think about a filter, I think like this, where we have, let's go to a new page. If we have some resistance, because our coil has some resistance, if we have some inductance, and if we have some capacitance, as what was displayed on the on the sticker on the filter, if you remember. And so if we write down the transfer function of this, the ratio between input voltage and output voltage of this filter in Octave. So let's use some values that we used before. So for example, use this 10 ohm of resistance, which might be meaningful, this 1 millihenry of inductance and some capacitance of, for example, this 1 nano, or 10 nano, but I will maybe go back to the 0.22 micro that we had before. And so now if we write the transfer function or this ratio between input and output voltage, it will be ZZ, the impedance of the capacitor, and then divided by the total impedance. So ZZ divided by R plus ZL of the inductor. This is what we had before, and ZZ. And I think this will not now be meaningful because I've not yet calculated ZZ, but this is this. And omega is not defined because I've not calculated it yet. So there's our omega. There is ZZ. There is ZL of the inductor is J times omega times L. Okay. And this is our transfer function. And so now if I plot this, figure 1, and we will once again do a semi-log x plot of this, and instead of the transfer function, I need to use this one here. So we nicely see the same behavior there. And the problem is, of course, that if you have filters with L and C, that there can be also some resonance, there can be also some amplification. And this resonance, this amplification, this is also what we see, what we nicely see here in this, in this measurement of this real filter here, using my PicoScope and using this differential probe. Unfortunately, this corner frequency here is at rather high frequencies already. And so I think I cannot go higher than this. And that's why we cannot have a nicer measurement of the real behavior of the filter at the point where it should attenuate. Yeah, but that's why these filters are so small, because L and C in there are not super large, and that's why these corner frequencies are rather high. But still quite nice agreement, at least the general behavior for this filter between these two curves measured and simulated.